Yes, well, thank you very much for inviting me to speak here. It's a bit of an odd day, I think, a little bit scattered thinking about the other things that are going on in the world, but maybe it is a good thing to just focus on mathematics and ignore all the other tragedies that may be occurring. So I wrote the title of this talk, and then Eamon was rightly very skeptical, being like, well, we've been trying to do this for an extremely long time, and it's called the Matrix Group Recognition Project. And so maybe my title was a little bit ambitious, but we are going to try and get some new information in this, but I'm going to really assume a lot of things. So in terms of you could say this is inspired a little bit by the Matrix Group Recognition Project, or it goes in that direction, but certainly this is a slightly different viewpoint on the whole subject. Now, what I'm going to talk about today is extremely classical in some parts. I mean, some of these things go back to Chevalley and the Seminaire Chevalley in the 50s and 60s, and so it's, you kind of wonder what you can really say, and certainly I'm coming to this very late in the game, and in terms of what I'm going to talk about, I was very much influenced and have learned a lot from everyone who was involved in the Chevy project, and in particular Frank Lubeck and Jean Michel. So I really want to just acknowledge those two people specifically before I start my talk. And actually, the theoretical part of this is all contained in one paper that I wrote by myself, but the actual implementation and the computational aspects were all done as joint work with Jean Michel while we were at the MSRI. Okay, so let's crack on. Okay, so I'm going to be working over an algebraically closed field, and I want to consider connected reductive algebraic groups. So I want to classify these up to isomorphism. So obviously connected here is extremely important, because otherwise I'm trying to classify all finite groups up to isomorphism, and that's quite hard. So I'm going to be calling this a CRAG throughout this talk. So what we want to do is to give a parameterization of the set of isomorphism classes of CRAGs defined over this field K. Okay, so this we have to be a little bit wary here. So when I talk about a connected reductive algebraic group, there are two ways you can think about this. You can think about it in terms of an algebraic variety. So you have to be wary about thinking about points. So we want to avoid really thinking about points in the field. So if you're in positive characteristic, then you can have abstract group isomorphisms. So this, you can take this group on the left, SLPK cross GMK, so where GM is the multiplicative group of the field, that's going to be abstractly isomorphic to GLPK. Okay, but they're not isomorphic as reductive algebraic groups. Okay, so because these aren't isomorphic as varieties. Okay, so we want to take into consideration these issues. I mean, even beyond anything, why might you be interested in this problem? Well, we've already seen why you would be interested in this problem in David Stewart's talk, because he invoked the standard hypotheses. So he invoked the standard hypotheses precisely because he didn't want to deal with SLP. He wanted to deal with GLP, because geometrically, GLP is much nicer than SLP. So you actually do really want to care about this if you're going to work in the level of algebraic groups. Okay, and it has interest for other reasons. Okay, so really we're going to think about, you can think about these things as group schemes, but we want to get something that's computational, and we also want to make enumerative statements, and so it's very convenient to work with another language, which is the language of root data. So we've already seen this before. Frank Lubeck has introduced this before in his talk, so let's just briefly recall what this is. So a root datum for me is going to be a pair of free Z modules, which are put into perfect pairing. So that means that one is isomorphic to the Z dual of the other. And you have a finite set of roots in X, and then you have an injection of the roots into this X check, so into the dual, which gives you the corresponding co-root. So at every root, you have a corresponding co-root, and they have this relation here. So if you take any, this is just going to be an aside. I'm not going to use the val group too much, but I do want to mention it. So whenever you to each root alpha, you get corresponding reflections. So these are invertible endomorphisms of X and X check. Okay, and they have these very simple formulas given by the perfect pairings. And exactly this condition that alpha alpha check equals 2, that's making sure that this is actually going to be a reflection. You want it to be an element of order 2. That's what that's ensuring. Okay, and so these things are going to be root systems, and you want them to be stable under the reflections. So if you look at you get a subgroup of GLX, which is generated by the reflections, and that's the corresponding Weil group. Okay. So this is all very classical. So I'm going to actually work with base root data. So it's inside a root system, you can always pick a simple system of roots. And so it's convenient to really think of this as being part of this data. Okay? So I'm going to assume I've fixed a simple system. And up to conjugacy in the Weil group, they're all conjugate. So it doesn't really matter which one we pick. Okay. So it's very convenient. So I'm really thinking about these two lattices, these two free Z modules. So I'm always going to just assume actually that I have fixed standard bases, EI and EI check. And so my perfect pairing, these are just going to be dual with respect to the perfect pairing. Okay, so I'm just going to assume this from now on. So I want to think about what a morphism should be between root data. So actually it's a very simple thing. A morphism between root datum, so it's actually a pair of Z-module homomorphisms, and one determines the other in that one has to be the transpose of the other with respect to this form. Okay? Now, to be a morphism of root data, you have to have that when you restrict to the roots, actually you get a bijection between roots, and it should biject the simple roots to the simple roots. So what this is telling you is that inside X, or X1, you can look at the lattice generated by the roots, Z phi 1. And this is going to say that if you restrict to Z phi 1, that maps isomorphically the lattice generated by the roots to the lattice generated by the roots. That's another way of really thinking about this. So there's actually a very nice little argument, I think, which goes back to Desmajeux, which says that actually these are compatible. If you just with these properties, it's actually compatible with this bijection we picked. So if you take a root, you apply phi and then consider the corresponding co-root, actually that's the same as taking the inverse of the transpose of the corresponding co-root. So this is just an aside. Okay, so if we look now, so I have the notion of a morphism, so I know what an isomorphism should be. It's just the usual categorical notion of an isomorphism. And so we can talk about the isomorphism classes of root data. And a very, very classic theorem of Chevalley, which goes back to the 50s and 60s, says that the isomorphism classes of CRAGs over a field K, that's going to be in one-to-one correspondence with isomorphism classes of root data. So of course, this is a bijection on isomorphism classes. And actually, so if you allow yourself to add a bit more information onto the left, this actually comes from an equivalence of categories. So actually, you can think of, if you endow your CRAG with what's called a pinning, then actually you get a correspondence between morphisms as well. So everything to do with the connected reductive algebraic group is actually completely just corresponds to one really in this language of root data. Okay, so let's just do two examples. So if I just take R direct copies of the field, the multiplicative group of the field, that's going to be a torus. And this corresponds to a pair, you just take ZR, and the roots are empty. Okay? Now, if you do GLN, okay, so the isomorphism class of GLN, that's going to correspond to the isomorphism class of this. So you take a free Z module of rank n plus 1, you take these to be the roots, these to be the simple roots, and then your bijecting, the corresponding co-roots are given like this. Okay, this is, I'm sure if you've ever done any calculation with algebraic groups before, you'll have seen this example. Okay, so what we want to do now is talk about a data structure. So how do we get this into the computer? So let's start with our base root datum. So if I take the simple roots, each simple root obviously can be written as a linear combination of the basis of x, and the corresponding co-root can be written as a linear combination of the basis of x check. And so if you calculate the inner product, because these are dual, what you find is that the inner product of alpha I and alpha j check, that's A times A check transpose. Okay. So the entries on the left, those are, you know what those are the Cartan integers. So this is telling you that A times A check transpose, so like A check be these matrices, then the product should be the Cartan matrix. So in terms of the computer, when we think about a root datum, we think of a pair of integer-valued matrices, both with the same number of rows and columns, such that the A times A check transpose is a Cartan matrix. Okay, that's all it is. So this actually tells you very clearly that a root datum gives rise to such a thing, and it's a little bit, and I think probably this was also a key observation of Frank, was that actually any such pair also you can get a corresponding root datum. These are actually, it's exactly the same statement. And going back is a little less obvious. Okay. Okay, so we're going to think about these root data like this. And now isomorphisms between root data are easy. You just multiply by an element of GLRZ. And now, of course, my talk should be finished, because, right, if I have a matrix, if I have an integer matrix A, well, you can always find a unimodular matrix such that AG is in the Hermite normal form. So the Hermite normal form will look something like this. You'll have possibly a bunch of zeros on the right, and then you'll be upper or lower, whichever which way you want to do it. You'll be triangular on the other side. Okay? So you may have come across, you may have used quite often the Smith normal form. The Smith normal form is not quite what you want to do, because in the Smith you're operating both on the rows and the columns at the same time. Here I only want to operate on one side, so I want to use the Hermite normal form. So now this is easy. I want to know, are my algebraic groups isomorphic? Well, I just calculate the Hermite normal form for both. If they're the same, they're isomorphic, and if not, they're not. But that's only testing for isomorphism. If you just pass me now this matrix in Hermite normal form, that doesn't actually tell me what it is. I mean, what is the group? So we want to, this is in essence the matrix group recognition project. It's not just about isomorphism testing, you actually want to know what the group is. Okay, so what we want to do is investigate this and try and get a nicer parameterizing set, nicer labelings. Okay, so let's just keep this definition up there. Okay, so in terms of GL3, this data structure is pretty easy. This is now just writing down what we had before. And the product now you can see is this, and this is the Cartan matrix of type A3. Okay? So what do you actually want to do? So actually what we're doing now is I have a Cartan matrix, and what you want to do is classify up to this equivalence all possible factorizations of the Cartan matrix. So actually when you think about it like this, it's maybe less easy to get a grip on it, because actually trying to classify factorizations of matrices is quite hard. It's very hard to say anything about the product. If you know what a product of two non-square matrices is, it's hard to say what the actual things are themselves. Okay, so we can take a kind of the simplest possible case, which is take the Cartan matrix of type A1, which is just a square matrix with a 2 in it. Now, up to this equivalence, there are actually only 3 possible factorizations. These are all the possible factorizations. One corresponds to SL2 cross the torus, one corresponds to PGL2 cross the torus, and the other one corresponds to GL2 cross the torus. Okay, and so this is kind of well known in the theory of algebraic groups. This is what's known as the semi-simple rank 1 case, which is a kind of important case that you want to understand. Okay, so I want to do first this. I want to do first semi-simple groups, because you need to have a reasonably good understanding of semi-simple groups before you can do the general case. Okay, so obviously, there are two extreme cases. Your group is either semi-simple or your group is a torus. Tori are easy. Tori are just uniquely determined up to isomorphism by their dimension. So once you know its dimension, you're done. Semi-simple groups, we have to do a little bit more work. But it's not so far. I mean, it's a classical and well-known result. So but let's kind of just go through it quickly. Okay, so what does it mean for my CRAG to be semi-simple? Well, it's going to be semi-simple if and only if it's perfect. So it's equal to its derived subgroup. In the language of root data, that's saying that X mod the lattice generated by the roots is finite, or equivalently, in terms of what we put in the computer, that means that my matrix A is square. You can also say that a check is square, or X check mod Z phi check is square. Okay, those are all equivalent. Okay, so if we extend scalars then over Q, then we can get Q vector spaces. Okay, and we can extend our perfect pairing to get now an identification between of QX check with the dual vector space of QX. Okay, so inside, why do I want to go over to QX? Because what I want to do is construct the weight lattice. So Frank already talked about the weights in his talk when he was talking about representation. So inside this vector space QX, you have the weight lattice. So it's just all vectors whose inner product with any co-root is an integer. So the weight lattice mod the root lattice is actually a finite group. Okay, and clearly your X lives in the weight lattice. Okay, so your X mod Z phi, that's going to give you a subgroup of this group lambda mod Z phi, which I want to call big pi, and I think I didn't do it, so let me write it. So I think I want to call pi lambda mod Z phi. Okay, so you have the fundamental weights. So these are a dual basis to the simple co-roots. Okay, and they have the property that the roots decompose in terms of the weights using the Cartan integers. Now you have this very nice theory of what are called minuscule weights. So minuscule weights satisfy this property for all roots. Okay, so actually it turns out that the minuscule weights are always one of these fundamental weights. So that it's identifying some subset of the fundamental weights, and it's very well known what these are. And actually, there's a lovely statement which says that you get a bijection between the minuscule weights and the non-zero elements of this finite group. So actually, you can just think about the non-zero elements of the finite group in terms of minuscule weights. Okay, so let's. Oh yes, okay. So I just want to make one comment. So I'm going to try and think about things in terms of minuscule weights. So I want to say when two semi-simple root data or groups are going to be isomorphic, well, they obviously have to have the same root system. So let's just assume that we fix a root system or a Dinkin diagram. That's done. And so now you're trying to understand, well, if you have the same root system, what's going to be isomorphic? So I need a group which is going to act and do all the work of calculating these isomorphisms. So you can introduce a positive definite, symmetric, bilinear, and non-degenerate form on this Q vector space. Okay, so think Euclidean inner product. So really, what this is saying is that the root system, as you know and love it in terms of Euclidean vector spaces, it's going to be a root system with respect to this form. Okay, so inside, you now have an orthogonal group with respect to this form, and you can look at the stabilizer of the roots inside there. Now, if you remember the formula I wrote down for the reflections, when you act by a simple reflection, you only add or subtract a root. So that means you're actually the Weil group will actually act trivially on this quotient group. Okay, so the automorphism group of phi, if you have an automorphism group of if you have something stabilizing phi, it'll actually induce an automorphism of the weight lattice. You can lift that to the weight lattice. So if you've ever done things with semi-simple algebraic groups, you'll know that if you have an automorphism or on an algebraic group, then you can always lift it to the simply connected covering group. Well, that's just this statement, that you can lift anything from the root lattice all the way up to the weight lattice. Okay? And this quotient is actually the automorphism group of the Dynkin diagram. So when we want to parameterize the isomorphism classes of these semi-simple groups, what I want to do is let this group act on this fundamental group. And it's the orbits that are going to give me the isomorphism classes of semi-simple groups. Okay? So let's just do an example. This is probably the most interesting one. If we do type D, there are 3 minuscule weights. And I've taken the extended Dynkin diagram, and I'm going to let the extra node represent 0. If I do that, then I actually just get the whole fundamental group. Okay, so there are 2 cases. So if n is odd, then this fundamental group is isomorphic to Z mod 4Z. So you only get 3 subgroups. So you get the adjoint, the simply connected, and SO in the middle. Now here, there is a graph automorphism of type D, but it's going to be inner in this case. The longest element is -1 times the graph automorphism. So actually, this group is acting as -1 on the fundamental group. So it stabilizes all the subgroups, so it doesn't do anything to the subgroup structure. So if n is even, then it's going to be Z mod 2Z, direct sum Z mod 2Z. So you now get something extra, because now you have these 3 subgroups of order 2. Okay, so you get SO, and now you get this half spin group. So now you actually have the graph automorphism. It actually does something on the fundamental group. So it actually permutes those 2 fundamental weights, and it means that those 2 subgroups actually give you the same group. Okay, so so in this instance, you're kind of forced that if you want to do some kind of parameterization or give some kind of labeling, you need to distinguish. You need to choose one of these fundamental weights, okay, and say which one you're going to use. Okay. So obviously in 2AN and 2E6, those are the other 2 simple groups that have a graph automorphism. They both also act as -1 on the fundamental group, so they don't do anything to the subgroups. Okay, so what I want to do now is think about a normalization process for semi-simple root data. So I want to get this into a reasonably normal form. Okay, so I'm going to assume I have my pair, and the product is going to be a Cartan matrix. Well, someone may have given you a really weird Cartan matrix that you don't like. But Cartan matrices are fairly well behaved. Root systems decompose as a direct sum of irreducible root systems. So that means that your Cartan matrix should be a corresponding product of blocks. And so you can just permute the rows and columns until you get it into block form. And let's say we order it so that it's lexicographic. So you go A, B, C, D, E, F, G, and then you can go up by the rank. Now, this matrix gives the weights the fundamental dominant weights in terms of the basis of X. You want to know which ones live in X, but that's now super easy. You just inspect the rows, and you just want to look for all the rows where every entry is an integer. No, I'm inverting over Q now, because this matrix is not invertible over Z, but it will be invertible over Q. So the entries may be rational numbers, but some of the rows will contain only integers, and those are the fundamental dominant weights that live in X. Now I want to normalize and get it into a canonical form, and so I'm going to use the Hermite normal form. So if I invert this now, I get the basis of X in terms of the weights, okay? And now I'm going to put that so it's in Hermite normal form. So another way of thinking about this is that you're changing the basis of, another way of thinking about this dually is that you're changing the basis of X check so that the co-roots are in a canonical form with respect to that basis. Okay, it's doing the same thing. But this now at least gives me, so let's say so for all your complicated possible semi-simple groups, you have a root datum, you have this automorphism group acting, and we just identify a bunch of fundamental dominant weights that allow us to pick out the isomorphism class, or the give a labeling to the orbits of the graph automorphism group of the Dinkin diagram on this fundamental group, and then I can get a labeling. I just take a root system and I get a set of fundamental dominant weights, and that identifies this thing uniquely. Okay, so that's how I want to think about semi-simple root data. Okay, so now this is very classical. So now let's try and think about the general case. So you want to identify a group up to isomorphism. Well, you should just come up with some invariants. Okay, and there are easy invariants you can write down. There's the derived subgroup. That's going to be invariant. There's the radical, which is also the connected center of G because it's because this is a reductive group. And then you have the central core, which is going to be the intersection, or what I would like to start calling the central core. If anyone else would like to adopt this terminology in papers, I'd be very ecstatic. Okay, so I want to now think about this. So let's just think of equivalence classes of triples. So semi-simple groups, a semi-simple group, a torus, and I'm going to take a subgroup of the center of my semi-simple group. And I'm going to put the equivalence relation on there is that there should be an isomorphism between the semi-simple groups, and it maps one subgroup onto the other. Okay, and the tori should be isomorphic. So you essentially know what this is. So this is, we've just described how to classify or parameterize semi-simple groups. Tori up to isomorphism are uniquely determined by their dimension, so it's just a number. And then you're talking about the subgroup of a finite group, but really a finite group that you understand very well. So these independently you can classify very easily. And this is going to give you now a partition of these isomorphism classes of algebraic groups. So you're going to be, right, you just pick the groups that have G as its derived subgroup, T is the connected center, and C is this central core. Okay. So now you have a basic problem where you just want to parameterize these sets. How many things can live in this set? Okay, well, if you think about this on points, you have a short exact sequence. So really this is just saying that an algebraic group is the product of its derived subgroup and its connected center. Okay, this is very well known. So I'm going to mimic this. So I'm going to fix a triple GTC, and I'm going to assume I have a closed embedding of this finite group into a torus. And now you can define a connected reductive algebraic group. So I want to kind of think of it as functorially. So it should take this the field to this group. So on points it does this. Okay, so this is going to be, my G is one of these. Okay, and now the observation is actually that you can now just parameterize this set in terms of the automorphism group of this finite group. So here you're going to get two subgroups of the automorphism group. So so you have a torus, and you have this subgroup sitting inside. So what should ought T C be? Those are going to be the automorphisms of the finite group, which you get from an automorphism of the torus, okay, that actually extend up to the torus. And ought GC, that's going to be the same. Those are going to be the automorphisms of this finite group that you actually get from this an automorphism of the semi-simple group. Okay, so this is now something that you should just be able to calculate. Okay, so for instance, I mean, if you had say if your semi-simple group was say SLN, then what automorphisms are you going to get? Well, you're just going to get the graph automorphism, and that acts as inversion on the center, and so you're just going to get the inversion map on the center in that case. So the ones that come from the semi-simple group are kind of very small. It's the ones that lift to the torus. So you're kind of asking now, when does a automorphism of a finite group lift to an automorphism of a torus? Okay, so let's just do an example. So if n is an integer, let's take mu n, right? So this is, think of this as a cyclic group of order n, and you fix a closed embedding into the multiplicative group of the field. Well, the automorphism group of the multiplicative group is a group of order 2. It's just there's only inversion is the only non-trivial automorphism, because this is an automorphism as an algebraic group. Okay, but the automorphism group of mu n has size Euler's phi function of n. Okay, so you clearly don't get everything here. It's not always going to lift, right? And in fact, the index is going to be just phi of n over 2. So you can rephrase this in terms of characters. If you go to the character group, so taking characters is an exact functor. So you can actually just think about this in terms of presentations of finite abelian groups. So you have a presentation of a finite abelian group, and now you have an automorphism of that finite group. When does it lift to an automorphism of the free group? Okay? All right, so this is basically the same problem. You have z mod nz, and let's just take this embedding. So if I only had one factor, then we know that only 2 of them lift. Well, now let's fix an integer coprime to n. So all the automorphisms of the finite group are just going to be multiplication by an integer coprime to n. And you can appeal to Bézout's identity. So Bézout's identity tells you there will be 2 integers such that ka plus nb is equal to 1. And now if you write down this matrix in SL2Z, that's an automorphism of my free group, okay, or of my free abelian group. And that will induce xi k, or multiplication by k, on the quotient. So when you have, if you only have one copy of z, it won't always lift. But as soon as you have 2, then it always lifts. Okay. So this really now goes back to work of Diaconis and Graham. So it actually tells you a very nice answer to this problem. So I'm going to fix a tuple, and I'm going to let this finite group just be a product of, I'm going to put it in its, written in its invariant factors, okay? Then actually the following hold. So if the dimension of T is strictly less than S, then this set has to be empty, which is just clear, because if you want to embed this thing into, if you pick a presentation of a finite group with a certain number of invariant factors, you have to have at least that many copies of Z to write it down, okay? Well, what if you have exactly the number of invariant factors? Then actually what Diaconis and Graham say is that the number of things in this set will divide Euler's phi function of ds. And what if you go one more? Well, everything collapses and you just get 1. There's only one thing. So it turns out that actually almost always these 3 invariants actually completely determine your connected reductive algebraic group up to isomorphism. Okay? So let's look at this as an example. So let's take G equal to SLN, and let's look at the center. So that's going to be mu n. So if the dimension of T is 0, obviously mu n can't embed in something that's 0-dimensional. Mu n does embed in a 1-dimensional torus, and then it's just this calculation we did before. This is just going to give you Euler's phi function of n over 2 number of non-isomorphic groups. And then as soon as you have more than 1 dimension, you're done. So an example of a group here in this class would be GLN. And then once you hit here, the only thing you can get is GLN cross a torus. Okay? So this is actually very controlled, and it means that you have a very a good chance of actually trying to parameterize things. There's very few invariants that you actually need to try and classify things. Okay, so I found this quite surprising. I think when I thought about the SL2 example, I thought maybe 2 times S would be a good bound to make sure you only got 1 and that everything would lift. But Diaconis and Graham really give you the exact answer, and it's even better than that. They give you an exact algorithm for calculating, to putting this into a normal form. So it actually gives you an algorithmic way to calculate what the answer. So maybe I'll just say I spoke to Percy at the MSRI, and he told me that he just did this for fun. It was just something that they were doing, and he was like, I had no reason to do it. It was just I was talking with Graham, and he was delighted that there was, that maybe like 20 years later, someone found a reason for this to exist. So I think this is a good advertisement. If you have a problem that you think is nice and you can answer it, you should just do it. It doesn't matter. It doesn't have to go in like inventiones or whatever. Just do it. It's fun. Like, okay. And maybe someone will use it later. Okay. All right. So, okay. So what we want to do now is think about a version of this construction at the level of root data. So this process now about how I want to identify algebraic groups is the following. I want to first write it in the form, I want to first think of it as a central product. So you have to first write it as a central product, and then I identify when two central products are going to be isomorphic. Okay? So the first trick is just to get this thing as a central product. Okay? Well, there are two things. You want to understand what this construction should mean at the level of root data, and then you want to understand how to write a root datum in this version. Okay? So central products. So actually, this isn't, if you do this calculation, it's not too tricky. So if you take a root datum and let's say a torus, and you take a finite abelian group. So what I'm going to assume is that you have two surjective Z-module homomorphisms to the finite group, okay? And the roots should be in the kernel of the one coming from the semi-simple guy. And that's because I need the roots to exist inside this lattice, okay? So what I'm going to do is just simply take the fiber product over B of these Z modules. And really, if you think about what you're doing about this, if you think in the language of groups, you're factoring out by something. You're factoring out by a finite group. And so if you think about this in terms of characters, you're factoring out, and so you need to put something in the kernel. So the characters of the quotient will inject into the characters of the original thing. So the original thing you start with is a direct product, and now you're quotienting out by something. So you're now identifying the characters of the quotient inside, and this condition is exactly that it's trivial on the quotient. Okay. So this is going to give this gives this construction, which we call the central product. And so what are we really doing? Well, on the one hand, you have kind of you have G cross a torus, and that's going to be the character lattice of that. And then on the bottom, you have like the adjoint group cross a torus. Okay, and you're considering lattices in between. Okay, so let's write a root datum. So we want to write this now as in this central product language. So we want to mimic these invariants that we had in the group. So you get the you're going to get the derived datum and the radical. So there are two basic constructions here that you want to do. So here you're going to get what I'm going to call phi top. So that's the rational closure. So that's the intersection. So it's going to be Qx intersected with, no, Q phi intersect Z. So I want everything such that if you take a power of it, then it's going to land inside X. So this is just going to be the torsion. This should be the torsion subgroup. So if you take this, this is going to be the torsion subgroup of this quotient. Okay, and then the other thing. Well, I can take perps, and so this is just the orthogonal complement. But it's just your complement lives over on the other side, because these things are in duality. Okay? Okay, and now you get a further invariant. So you have to see this, this central core. And so it's actually coming from the direct sum of these two lattices. So that's going to live in there, and the quotient is of X by the direct sum. It's actually not going to be the whole thing, and it's finite. And actually, it turns out that if you have the group corresponding to R, then this quotient is going to just be the character group of the core. Okay. Okay. So now you have a central product. So you take B. You have natural projection maps from the characters here and the characters here down to B, and you can form this central product. And now there's just a natural map from X x to this thing, and it's an isomorphism. Okay, and so this gives you a way to actually write it down. Okay, so now as before, you're going to get a partition of root data based on equivalence classes. So you're going to have semi-simple root data. You're going to have tori, and now you're going to have some submodule which in X which contains the roots. Now this equivalence from before, you have the group of graph automorphisms acting on the fundamental group of the root system. So that moves all these x's around inside in the semi-simple case. And so let's say you fix an x, and now you're taking another invariant, which is the k's. So inside the group of graph automorphisms, you take the ones that fix x, and then that'll act on all these k submodules. Okay, so you're just adding this extra ingredient. And you want to stick as close as you can to the semi-simple side because that's where all the structure is. There's not a lot of structure in a torus. Okay, so how do we see the derived root datum and the radical? So for the derived datum, well, you take a unimodular matrix and you put A check G inverse transpose into Hermite normal form. If you do this, so you're basically changing a basis so you can see easily those things which annihilate the co-roots. Okay, so you slice by you now just slice. You take the first n rows of this matrix and the first n rows of this matrix. That should be A check, and this will give you the matrices for the derived datum. Okay. Now, we know how to normalize our semi-simple root data to put them into a normal form, so we just normalize. Okay? We use the process from before. And now what we're going to do, because we need to keep track of all this information, we're going to store the projector and the change of basis matrix. Okay? So we keep track of all this information because we need to keep track of all these projections into quotients. So we keep track of the projector and the new basis. Okay, and so for the radical, you do the same, but you now do it for A instead of A check. Okay, and again, you're going to store the projector and the basis. Okay. Okay, so if you take this example from before, I mean, this example, when you write this thing down with GLN and you feed it into it and ask it for the Hermite normal form, I mean, it's so nice the way you've written everything down that it just gives you something super canonical. So basically, when you calculate this thing and you look at this new basis that it's going to give you, it's just going to pick out the first basis vector, and then the rest you see here are basically minus the roots. Okay. So now, if we concatenate the two bases that we found, we get a basis for this direct sum, which was this invariant that we wanted. Okay. So you can put this together and get the direct sum. And now you can use the Smith normal form. Now you do want to use the Smith normal form because you want to calculate a presentation for this quotient, and you can use that to get projection maps into this quotient. Okay, and so you can use these. You now have this projection map into this finite group, and then you have these projection maps into the radical and the derived datum. Okay, and now what you want to do is you have to do some identifying, and you now know that your two things essentially are going to differ up to an automorphism of this finite group, and you're going to use the Diaconis-Graham algorithm to normalize that to pick out this invariant that you're looking for. So this gives you, it's a little bit involved, but it gives you a way to actually write down some invariants and actually calculate a label for this isomorphism class of connected reductive algebraic groups. The only problem is that this maybe doesn't do exactly what you want it to, and the issue is because when you write it down in this way, for instance, let's take SL3 cross, let's take GL3 cross GL5. When you take the derived subgroup, that's going to be SL3 cross SL5. Its center is mu3 cross mu5, but that's isomorphic to mu15. And in this process, you're going to want to put everything, you're going to want to put all those centers together, because you have to write things in terms of the invariant factors. So when you do that, you're going to gather all of these things which were kind of nicely laid out in your algebraic group. You're going to squish them all together, and then you're going to calculate some invariant. And maybe it's not so clear exactly how the invariants correspond to the groups you would like to see. So I don't think this is a perfect solution, but it's at least a solution towards this problem. Okay, and I will stop there before Eamon kills me. So you have like two projection maps. So you have two projection maps from, so you have a free Z module, and you have two presentations for a finite abelian group, and you know they're going to differ by some automorphism of the finite group. And so what you want to do is calculate. So Diaconis and Graham tell you how to kind of apply automorphisms of the free group to put that into a semi-normal form. Essentially, you have kind of, you can calculate just one invariant. So actually, they tell you that the only thing you have to look at is you can apply automorphisms of the free group until you get down to an automorphism of the smallest invariant factor, and then you're stuck. You can't do anything more, and that's going to be the thing that pins out what's going on there.
Constructed some groups which are similar to GL in type A, so which has the property that the divided subgroup is simply connected, and one connected center I get the joint group.
Yes.
And it always works. I mean, it's easy to see from what you just described. It always works by adding a one-dimensional torus and then doing some normal form and finding a root datum for this, or in the even any case in the two-dimensional torus.
Yes.
So from your description, is it clear that the group I constructed this way is well defined after isomorphism?
Yeah, so it's going to tell you that there are so essentially this is also very constructive. You can use these central products really to just write everything down, and it will tell you that. I mean, in that case, yeah. So there are all these kind of like fake GLNs, if you will. Like they have SLN as the derived subgroup. They have like a smooth and connected center, but they're not GLN. And that's all these ones in this phi of n mod 2, and that in the SLN case. And that's basically saying that there are phi of n mod 2 isomorphism classes of those groups. In type A. So in general, for the other types, it's basically there's only one way to do it, up to isomorphism. Yes. From this, you basically know that that's essentially unique. So this is my illustrious collaborator and I are hoping to finish this this week. So it's kind of almost there, but I think we probably need to discuss a little bit more.